welcome to Lesson 4 on equilibrium. Our lesson objectives: define and explain equilibrium, including phase, solution, and chemical equilibrium. In a system at equilibrium, both the forward and reverse reactions are taking place. So if you look in this animation here, we have our reactants on the left and products on the right. Both the forward reactants forming products is occurring, as well as the products, the reverse reaction, are breaking back down into the reactants. And so we show that both reactions are taking place with a double arrow, as you can see here. So N2O4 is forming NO2, that's my forward reaction, but also NO2 then is going back and forming N2O4. And so once we get to equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. That's the equal part of the equilibrium. And so you can see here we have two reactants, we have A and B, and they're forming this product or this compound AB. And so the rate at which that is happening, as you see here, this animation, equals the rate at which AB is breaking back apart into our reactants, individuals A and B. And so it's said to be dynamic. It's in constant motion. So a common misconception is that equilibrium, everything stops, and that's not the case. Both things are occurring at the same rate, and so it looks like nothing is changing. But there is still a continuous motion. So let's look at a system as it approaches equilibrium first. So we start out with just N2O4. Initially, the rate of the forward reaction is going to be faster than the reverse reaction, as you can see here in this graph. So initially, we have a much higher rate for N2O4 and a much lower rate for NO2. And then as they start to approach equilibrium, you'll see that the rates of N2O4 starts to slow down and NO2 starts to increase. And then once we get to equilibrium, we'll see that the rates become equal, as you can see in the graph here. So equilibrium is this dotted line here. So the rate at which this forward reaction equals the rate of the reverse reaction. And a good way to think about that is if you went to the mall on the down escalator and you were walking up or running up at the same speed at which it's going down, it's going to appear that you're not moving at all. But in essence, the escalator is still moving and you're still moving. It just happens to be at the same rate or the same speed. And so that's why it's a good example of dynamic equilibrium. So let's also look at what else happens at equilibrium. Well, if you look at this picture here, if I'm pouring water in at the same rate at which the water is leaving, then the amount, the concentration of water, this level here, is not going to change. Because as it pours out, it's also pouring in. So like the picture, at equilibrium, the amount, the concentration remains constant because the rates are equal. If I am making NO2 as fast as NO2 is making N2O4, then the total amounts do not change. You can see that in terms of concentration. If initially I start out with N2O4, which is very high, as that starts to get used up to make our product NO2, NO2 starts to increase. And eventually, the rates become equal. And when they become equal, the amounts don't change. They stay constant at equilibrium. So let's look at some different types of equilibrium we've experienced throughout the year thus far. So phase equilibrium is during a phase change. So the rate of the forward phase change equals the rate of the reverse phase change. So for example, the rate of vaporizing equals the rate of condensing. So let's look at an example of that. If we have water in the liquid state and it's at a phase change going to water in the gas state. So the rate of the forward reaction where liquid's going to gas, vaporizing, is equal to the rate at which the gas is turning back to a liquid, which is condensing. And so if you put it into a closed container, we could see that. We'll see that the liquid level is not going to change over time because we're at equilibrium. The rate at which the liquid is turning to a gas or a vapor equals the rate at which that vapor is condensing back into a liquid. And so again, the concentration remains constant over time. Now let's look at solution equilibrium. So if we have an unsaturated solution, this is not an example of equilibrium. It has not reached equilibrium yet because it dissolves more than it precipitates. So the rate of dissolving is greater than the rate of precipitation. We do reach equilibrium once we get to saturation. When a solution is saturated, it's at equilibrium because it dissolves and precipitates equally. So the rate at which it is going into solution equals the rate at which it's coming out of solution. In a supersaturated solution, since we're going to heat the solution up, this is also not at equilibrium because now, once you let it cool, it's going to dissolve less than it's precipitating out. So it's precipitating out more than it's dissolving. And a good example was the rock candy experiment that we did in class. And lastly, chemical equilibrium. Equilibrium is achieved when the rate of the forward and reverse reactions are equal, so the concentrations become constant, as we saw in that previous example. So let's check your understanding. Can you define and explain equilibrium, including phase, solution, and chemical equilibrium? At this point, you should be able to define and explain equilibrium, including phase, solution, and chemical equilibrium.